Okay, so here's what we were talking about last time. We were talking about Stokes' curl theorem. So we did several things with this. In particular, notice that Stokes' curl theorem is a way to relate line integrals to flux integrals. In particular, just to emphasize, really big deal, make sure to not get this wrong, boundary line integrals, right? Very importantly. Circulations, specifically. And fluxes of not your original vector field, but the curl of your original vector field. Okay. All right. So we saw some examples, and then I made this observation about how, flashing back the fun with their line integrals, you can reinterpret gradient. You can't call it a density quite, because it's not a scalar, for one thing, right? But it's an oriented density in the sense that dx is an oriented size, if you will, if you don't think inflexibly, right? And if you interpret just the same way from Stokes' theorem, and we went through these details last time, so I'm just sort of summarizing, you get an interpretation of curl. And this is the one that we really needed. This is the one that's harder to visualize. I mean, the gradient, we already know what the gradient looks like from chapter 2, right? That was old news. But working by analogy, right, having set up a point of view for gradient, I get a point of view on curl. It's oriented circulation density. And specifically, curl, having a magnitude and a direction, the magnitude tells you how much rotation is happening in some sense. Is it a lot of rotation, or is it kind of a slowly rotating fluid? How rotating is it? And the direction tells you in what direction is that rotation happening. And of course, with rotations, what that means is what is the axis? What is the axis that the rotation is around? Right? And you could have a rotation around a horizontal axis like this, or you can have a rotation around a vertical axis or whatever. Okay. So ultimately then, this picture. So curl, again, that vector tells you the axis that the rotation is around by virtue of its direction, and in some sense how much rotation there is by virtue of its magnitude. Okay. All right, and that's where we left off. So we're going to talk about some physical examples now, and this is first one's hopefully very familiar. You may recall that if you have a fluid, I like to think of a river, like the surface of a river, right? And if you want to know how the water is moving, well, the water is moving as described by a vector field. That's how we use vector fields to represent the flow of water, very often just giving the velocity, right? Well, if you want to know what the leaf's velocity is, the leaf is going to do exactly what the water does, and so the vector field itself tells you the velocity of the leaf. That's just kind of I'm going to call it a freebie. But the much harder question, and this is a reminder, how would I understand how the leaf is rotating as it goes downstream? Does it kind of rotate sort of like that as it flows, or does it rotate more kind of like this as it flows, right? And Green's operator gives us that. Green's operator is a measure in some sense, let's not worry about units, in some sense it's a measure of how much is there a rotation in the motion of the fluid. Okay. All right, so let's talk about curl then. Curl is just the three-dimensional version of that. So as we just discussed, of course, the actual motion of if you have like a floating balloon and you want to know what its velocity is, well, the vector field that tells you the velocity of the air. Well, the balloon's going to do exactly what the air does. So whatever the velocity of the air is, that's the velocity of the balloon. Well, of course. The more subtle, sophisticated question: how is the balloon rotating? What sort of an axis is it going to be sort of spinning around? And, well, again, it's going to do what the air does. Curl of the flow field tells you how the air might have some sort of a rotational element in it, the balloon's going to do the same thing. So the curl gives you, in some sense, the rate and the axis of the rotation per that picture. What do you think? Everybody buy it? Okay. All right. Okay, now here's a less intuitively satisfying example, but something that engineers probably have more directly to do with. Not a lot of balloon rotation engineering problems out there, probably. But currents and magnetic fields. So E&M's a big deal, right? In engineering, all y'all who are engineers anyway are going to have a strong understanding of electric and magnetic fields. We already talked some about electric fields, and it just turned out that Gauss's divergence theorem was this awesome tool for understanding electric fields, at least from a certain point of view. Let's talk about current. Y'all probably remember the idea of current in a wire, right? If you've taken a physics class anyway. If you haven't, don't worry about it. But in everybody's first time seeing current, the idea is you have a wire and there's electricity is flowing through the wire, right? And okay, current says at a particular point in that wire, as the current flows, as the little charged particles flow, how many particles per unit time are flowing past that point on the wire? So it's a flow rate. Well, that assumes the charged particles are all in a wire. In general, they're not necessarily. In general, charged particles can be flowing along just freely in space. And maybe they're in a wire, but they don't have to be. Right? So what we have here, this is this idea of charged particles not confined to a wire, but just kind of flowing through space. And we represent that with what we call the current field. It's not a current constant, right? I mean, if you have a wire, the current is just a constant. It is what it is all the way through the wire. Here, it's a vector field that can vary depending on where you are. Just like air can flow in various different directions, charged particles can flow in various different directions. Get weird. So anyway, we call that J. That's our current flow field. Now, a fact of the physical world. Don't ask why. This is empirical, right? If you want to know the why, it gets real philosophical and speculative, right? But the fact is empirically noted that when charged particles are flowing, that creates something called a magnetic field. It is a weird feature of our universe that we live in. And magnetic fields kind of tend to go around in circles-ish. That's an overstatement. But something along those lines, perhaps, given how I have my current field drawn. Okay, so weird, but current creates this magnetic field. Okay. All right. So now with that in mind, let's imagine a scenario where we have a loop of some sort, let's say about like that. And let's imagine that we have a surface inside of that loop, as it were, or to say it differently, suppose that my surface's boundary is that loop. And there's a couple things that we can talk about on that loop and in that surface. On the one hand, we can talk about how much current there is going through that surface. Keep in mind what current is. Current says how many charged particles per unit time. Typically, you think of it as the currents in a wire, and there's a spot on that wire, and you're watching the charged particles go past that spot. Here, we have an entire surface, and we're interested in how many charged particles are flowing through that surface. It's literally flux. Okay. All right, so that's one thing. that we can talk about. Another thing on this picture we can talk about is, well, we've got this magnetic field. We already discussed how the magnetic field is going to kind of go around. And again, that's reality. I didn't do it. I don't know why that it is that way. It just is what it is. Magnetic fields kind of go around, and you could reasonably ask how much circulation of the magnetic field is there around that loop. And you can just straight up measure these things. And empirically, what they find is that they are proportional. This apparently is how the world we live in works. The magnetic circulation is always proportional to the charge current. All right, so now having written that down, let's remind ourselves that aside from this constant that's on both sides, along the top line, all we have is that current is a flux. Well, of course it is. Current is, reminder, stuff per unit time flowing through your surface. So again, literally computed as flux. That's how you compute stuff per unit time flowing through a surface. So that's, again, just a kind of, dare I say, a definition. And then this line down here, of course, is just Stokes' curl theorem. So what we have, now you've noticed, I'm sure, how this little rectangular layout is structurally very reminiscent of the rectangular layout that we made an analogous argument with the Gauss's divergence theorem, and we were talking about gravity and gravitational flux, and the physics was all completely different, but the structure is really, really similar. And we make an analogous argument and conclude that this must also be true. So this fact here about magnetic circulation and current is empirical, but then fancy math involving Stokes' curl theorem allows us to reinterpret that as a statement relating the curl of the magnetic field and the current flow field itself. So seemingly two very different statements. Again, at first glance, not seeing the argument that we have here, it would seem that these are four separate things, right? But they're really just the same statement in some very meaningful sense, given how Stokes' curl theorem connects them. Okay. So again, even though these are different equations, we consider them both to be Maxwell's fourth equation, at least in the way that I like to order Maxwell's equations. So same equation, two different versions. Is that cool? Okay. All right. Now, quick reminder. Everything on the screen here is an absolute rip-off of what we wrote down back in Chapter 6. And I'm just going to remind you really quick, this is about how you do a local test for path independence. And we had these three statements that are, we pretty quickly realized that these were all equivalent. Being a gradient, not hard to show that means your vector field is path independent. It's not too hard to believe or even argue that vice versa as well. And of course, it's easy to see that path independence is equivalent to a statement about closed line integrals being zero. All this stuff here we established way back. Right? Okay. And then there's also this little pair of statements, and also independently pretty easy to see why these are equivalent. I mean, after all, this is talking about some function, I'm calling Green's operator, some function where the double integral is always zero no matter what domain you pick. And how could that possibly be? What functions do you know where the double integral is always zero no matter what domain you pick? I think zero is the only one among continuous regularity issues, again, not our problem. So two different sets of statements, and notice, though, that they are connected, and I can connect one to the other by way of Green's theorem. Green's theorem telling me, as it does, that closed vector line integrals aka circulations, can be computed as a double integral of Green's operator. And so again, I'm not going to spend time on this because we went through all the details before, but Green's theorem was the foot in the door that connected easy observations about path independence to a couple of easy observations about Green's operator, thus giving us this very valuable punchline right here that if you want to know if a vector field is a gradient, aka if you want to know if a vector field's path independent, take your pick, easy test. Compute Green's operator. If you get 0, cool. You win. This is in R2, by the way. Okay, so we did all that. Then I stated, but didn't prove, that there was an analogous argument for R3. And I just kind of asserted that in R3, it's the curl. And I didn't give you any reason to believe it other than any possible trust you may have in me. And here's the argument. Now that we have the proper tools. These three statements, just like in the previous case, these three statements are the same. Highly analogously, these two statements are the same. Now it's a different kind of an integral. This isn't a double integral anymore. It's a flux of a vector field instead of a double integral. But again, this thing in here happens to be curl, whatever. This thing in here, the vector field for our flux, if the flux is always 0 for every surface, you always get 0 for the flux, I think that vector field has to be 0. What other vector field could possibly do this? Okay, so again, we have this green group of statements. We have this blue group. What's the connection between these? Well, it's exactly Stokes's curl theorem. Right? And conveniently, just kind of perfectly, Stokes's curl theorem is exactly the thing that connects circulations, right? Closed vector line integrals, circulations, to fluxes of the curl vector. And so we get, again, what we already stated, but now we have a justification for it. Thank you, Stokes's theorem. Here's how you tell if you have a vector field and you want to know if it's a gradient, you want to know if it's path independent in 3 dimensions, no problem. Compute the curl, see if you get 0. If it is, then you win. No problem. Okay, so beautiful how Stokes's theorem really does play a role here that's so extremely, if I can get this thing to cooperate, there we go, so extremely analogous to what Green's theorem did right there. Okay. All right. Okay, here's another analogy. This is one of my favorites. I think this is one of the most underappreciated ideas in multivariable calculus. Most textbooks don't even cover this, including ours, as I recall. And I think that's an outrage. It's extremely useful. I use this a million times when I was undergrad doing physicsy kind of stuff. And anyway, so let me not get ahead of myself. First, a quick reminder about path independence. Remember that if you have two curves with the same starting point and the same ending point, very important condition. They have to have the same starting point. They have to have the same ending point. If that's the case, some vector fields have the property of path independence, meaning you'll get the same value for this line integral that you will for that line integral. Wow, it's weird, right? Weird that would work out. All you need for a path-independent vector field to be able to conclude this, that these two curves here, mind you, let's see here, wrong color. These two curves, all you need is for them to have the same boundary points, same start, same end. Path-independent vector fields would give the same value for the line integral. I emphasize, most vector fields do not have this property. This is a special property. Only some vector fields have this property. Again, we talked about specifically that these are gradients, and or said differently, Green's operator or curl, depending on your dimension, has to be 0. Okay, but that's what path independence is. And then there's this alternative formulation of path independence that instead of comparing two different curves, you can say, look, when you give me two curves, I can kind of combine them together to make one curve, a closed curve, in fact, by going along the first curve and then backwards along the second. And an alternative phrasing of path independence is that that closed line integral, that circulation, in other words, would always be 0. So different phrasing, right? Different way to think about it. How are we doing? Okay. So again, old news, we already knew this. All of these ideas, one dimension up, still work. It's amazing. There are special. So let me go through it again. New stuff. There are special vector fields called surface-independent vector fields. Surface-independent vector fields are ones where if you have a shared boundary curve, so two surfaces. Two surfaces. My hands here. If the two surfaces have the same boundary curve, if they kind of meet together like this, like you're trying to, hold a fly in your hands. Right? Shared boundary, two surfaces. There are what are called surface-independent vector fields that will give you the same value of the flux, no matter what surface you pick. Just like path independent will give you the same line integral no matter what path you pick, as long as you fix the boundary. These vector fields will give you the same flux no matter what surface you pick, as long as they have the same boundary. Okay. Boundary, of course, now if you're talking surfaces, a boundary is a curve. Okay. And of course, we could rewrite this because, after all, the one surface and the other surface taken together, but we got to deal with the orientations. I'll come back and talk about the orientations in a second, where that minus sign comes from. But two surfaces with the same boundary, again, look at my hands, make a single surface that is the boundary of something else. Right? Or they are a surface with no remaining boundary. Thus, the fly can't get out. Right? And in this phrasing, surface independent would mean that the closed boundary flux is 0. So all of the same ideas, it's totally analogous. It's the exact same. It's a total ripoff of the idea of path independence. Okay, so now I have yet to address when this happens. Right? Under what circumstances is a vector field surface independent? Are there any vector fields that are surface independent? How would I know if a vector field that comes to me is surface independent? A lot of natural questions that we'll want to talk about. But before I do, let me take a pause. And does everybody at least see what I mean by surface independent? Everybody on board? As long as you get the right boundary, pick whatever surface you like. Okay. All right, so let me address the question, are there any surface-independent vector fields? And in fact, yes, there are. In fact, Stokes's curl theorem does this for us. And the punchline is, all curls. You got to worry about regularity stuff. So yes, they have to be continuous. Let's not worry about that. But all curls are surface independent. Weirdly. Now, I owe you a justification of this. I can't just go around making outrageous claims like that. How do I know curls are surface independent? Well, let's think about that vector field F being a curl, right? And now notice what you're looking at here. This right here now is a flux through some surface of a curl. Flux of a curl. Where have we heard flux of a curl before? Flux of a curl. Oh man, that's further back than I thought it was. Sorry, there we go. Flux of a curl is the right side of Stokes' theorem. Right? So a flux of a curl can be computed as a boundary line integral of that original vector field. So now back to where we were. Flux of a curl computed as a boundary line integral over the boundary of our first surface, that is, our boundary of S1. Okay, now wait a second though. That's this one. This one's computed by that formula. Now, next question: how would I compute this line integral? This line integral. Okay, flux of a curl again. Right? It's still a flux of a curl. It's still going to be computed with Stokes' theorem on the boundary of S2, which of course is, by assumption, the same as the boundary of S1. If we're looking at two surfaces, S1 and S2, with the same boundary, then they will get the same value of the boundary line integral that comes up in Stokes' theorem. And so that's how I know that these integrals are equal. These integrals are equal. I get surface independence. These are equal because having the same boundary means they have the same boundary circulation. Oh, there you go. So not only are there some surface independent vector fields, there's a bunch of them, all the curls. And by the way, this goes both ways, and this next statement is much harder to prove. Don't try. But not only is every curl surface independent, but every surface independent is a curl. Goes both ways. Again, regularity issues aside. Okay, so neat facts. Cool new property. All right. Now, how do you tell? Right? Some vector field comes to you. You kind of dig this idea of surface independence. I got an example coming up to show you where we'll make use of this computationally. How would I tell if a vector field is surface independent? Now, y'all probably recognize already this layout right here. Doesn't that layout look familiar? On purpose, because I want y'all to notice and I want y'all to see how these different operators and different objects play analogous roles. And first observation, we talked about these three properties of surface independence. Every curl is surface independent, and vice versa. Surface independent can be phrased in terms of closed fluxes being zero instead of shared boundary fluxes having the same value. So again, three totally analogous to what we saw before. Three equivalent formulations that we've already established. You'll notice over here another two statements that are pretty easy to relate to each other. Again, it's the same story. If I have some scalar valued function, divergence in this case, whatever, but some scalar valued function, all of its triple integrals are always zero. Come on, how's that possible? How can a function, all the triple integrals are zero, the function must be zero. Okay, so nothing particularly outrageous has happened here. I have these green statements that connect to each other. I have those blue statements that connect to each other, and I can connect them by way of Gauss's theorem, which is exactly the tool that I needed. After all, Gauss's theorem says that closed boundary fluxes are triple integrals of divergence. And so again, we end up with a test. If you want to know let's see here. If you want to know, is my vector field a curl? Is my vector field surface independent? How do I know? How do I tell? Compute the divergence. See if you get 0. If you do, then yes, indeed, you have a surface independent vector field, and feel free to play surface independent games. All right, let's see this in action. All right. Let's see here. I need to zoom back. Yeah, here we go. Now, this is got some geometric challenge to it. It's the nature of the beast. This course is pretty naturally and unavoidably geometric. Right? And I just can't change that. So before I get into the question, I want to talk just about the surface for a quick moment. Let's talk about what this surface is. How do I figure out what that is? How do I draw it? What is it? And very often students get this wrong. This is a dangerous little landmine. It's so easy to mess this up. As follows. That's a paraboloid. Y'all know paraboloid. Well, it's an elliptical paraboloid, but y'all know the deal with that old Chapter 2 methods, and you can do like that, right? And then we're looking for the part where z is greater than or equal to zeros. Okay, well, here's where z is 0, and so I want the part above that. And so you're very naturally seeing those two players. Very naturally, you might be inclined to say, well, I'm going to draw that for the paraboloid, and this is the cut that z equals 0 plane makes through the bottom. Now, what have I just drawn here? What I have just drawn here, I am in danger of tricking myself by my own drawing, because it looks like that I have kind of an upside down bowl, and then there's a face on the bottom like this. It's kind of what it looks like. You can see it right in the picture. What the picture looks like. This looks like a closed surface. My picture has deceived me. This is in fact not a closed surface. So very importantly, look at the phrasing of the question. S is part of the paraboloid. It's just the part of the paraboloid. This business about z being greater than or equal to 0 is a clarification of which part of the paraboloid we're talking about, right? But it remains. The surface itself is just part of the paraboloid. So this is not an upside down bowl with a flat base. It's just an upside down bowl. That's it. This is an open surface. So let's take a moment to make sure everybody's comfortable with that geometry. Does everybody see what I'm saying here? Okay. Really important. I mean, such a big deal because notice that what the question is asked. The question, going to the question now. The question says compute the flux through this surface. If this were a closed surface, if you were to step on the landmine, mistakenly confuse yourself into thinking this was a closed surface, then you'd think, oh, well, this is boundary flux, and you just write down the divergence theorem, and boom. And that would be 100% all wrong. Sympathetic, but wrong. And that's such again, super dangerous because it's, anyway. We've seen things like this before, where nothing that the student has written on the page has any validity, and if nothing on the page has any validity, there is no partial credit, right? It's just not. You can't do it. So you have to be very, very careful about this. Please be ultra careful. If you're not entirely clear on the dangerous distinction that I'm drawing here between what this surface actually is and what my picture kind of might almost fool me into believing. Talk to me after class. Let's take some time. Let's get that clarified, right? But that's an important distinction. This is not a closed surface. Okay. All right, so let's compute the flux. Now, first thing you might be tempted to do is to say, well, hey, look, I see my surface. There's a nice, easy equation. It's just a polynomial. It's a graph. It's not even that hard to parameterize because I can use the graph parameterization. And my vector field, okay, all right, it's a little ugly. But it's not that. It's all polynomial also. It's just a slightly ugly polynomial. It could be worse. And you could be tempted to take a deep breath and plow forward with a parameterization. And you get an answer there, but it's much easier to argue as I'm about to. And that is to notice that my vector field is surface independent. It's really not obvious. At a quick glance, it's certainly not my geometric intuition that's telling me this, right? That's a weird vector field. I don't know how to draw pictures of this. I don't know what it looks like. But I don't need to. That vector field, I can compute the divergence. I get 0, and that means surface independent. Citing this theorem right here. You take the divergence, you get 0, and surface independent. Is that cool? Okay. This is a massive win. Massive win. I can change my surface. I get to pick any surface I want. I have a lot of imagination. I can think of a lot of different surfaces I'd rather do than this one. Right? Now, before we go too crazy, of course, if you're going to use surface independence, don't forget, as we wrote like here, surface independence says, sure, change your surface to any other surface, colors, to any other surface you like, but you do need to make sure that that new surface has the same boundary as the old surface. Right? So I'm going to have to look back at my picture here. I'm going to have to think about the surface that I'm given. What is its boundary? And then what other surfaces can I think of that have that same boundary? All right, now keep in mind our surface, we've talked about how our surface is kind of an upside down bowl, right? And upside down bowls, well, the boundary is going to be sort of the lip of the bowl. And in particular, I'm going to draw it down here. It's that right there. Right? Everybody happy with that? Just think about the geometry of that surface, where it sort of ends. It's, that curve. Now I'm gonna commit a little bit of a math crime here. I'm gonna momentarily ignore issues of orientation. We'll come back and talk about orientation in a second. But I want y'all to see the big picture of the solution first, and then we'll get to the orientation. So that surface has that boundary. Now I get to pick any new surface that I want, and instead of this given green surface, my new surface that I'm going to pick instead is, I'm going to pick this, what I have shaded in gray down there. It's the easiest choice. There's lots of other surfaces that you could pick. All sorts of weird things, I suppose, as long as they have this same boundary. All good. But I'm going to pick the nice, easy one, that blue surface right there. Is everybody with me? Okay. All right. Well, again, path independence. Surface independence tells me that these two integrals are the same. I don't need to deal with that green surface anymore. I'm just going to throw that away entirely. I'm not concerned about the green surface anymore. I know right here the blue surface is just as good. And I like it better because it's flat. Right? And easy to write down the normal vector. The normal vector ends up being that. We'll talk about those details momentarily. But you can certainly see it's a vertical normal vector. And let's see here. Our vector field was color choices. I will use red. Our vector field is that. And so let's do this dot product, F dot n. So this dot that minus xy. Nothing to it. And so on that surface, my integrand is just minus xy. And I claim that's an easy integral. I'm going to leave the details for y'all. This is a nice exercise, but this integral here is 0 by symmetry. So you want to think that through. Reminder, we have an odd symmetry theorem for scalar surface integrals. This is now at this point we've done the dot product. This is a scalar surface integral. And I claim that surface has two different symmetries. Conveniently, this integrand also has two different symmetries. Pick your favorite. They both work. Again, good exercise to go through and think through those details. Everybody on board? So aside from orientation, we're done with this example. And notice how much easier this was than what it would have been had we done this the old-fashioned way, right? If we had parametrized and plowed forward, we would have been computing lots and lots of tedious computational stuff. Look how little computation there is here. I had to compute divergence, which was trivial, right? Effortless. And I, a couple of words, in recognition of surface independence, and just realized that I could transform to a different question that falls apart in our lap. Way, way better of a solution. Everybody see how nice this is? Okay. Right. Okay, so let's talk about the orientations. There are some little subtle, geometric challenges in here, and again, I can't change the fact that the geometry is what it is. So, okay, starting back with my original surface, we had this surface right here, right? And notice it says right here, oriented downward. So now I got to figure out what oriented downward means. Keep in mind there are two different orientations on any given surface. Our orientations here are what you might call upward. That's one option. And then there's the orientation like this that I think pretty naturally would be the one that we would call downward, right? So between the orange and the blue, all the blue vectors are somewhat upward. All the orange vectors are somewhat downward. Downward must mean the orange one. Is that cool? Everybody happy with that? All right, so oriented downward means that my normal vectors are, what you might want to call inward, I suppose. Again, it's a little sloppy to call it inward, but nobody's confused if you say inward. Okay, so now what does that mean about the orientation on the boundary? Well, okay, our boundary is clearly this purple curve right there. Which way does the orientation go? Remember, we have rules for this. If you have an oriented surface and you want to know the orientation that results on the boundary, we have a right-hand rule. So you use your right hand, you take your thumb, you point your thumb in the direction of the normal vector. So, by the way, my intention of what I've drawn here is that we're looking at a point on the near side of the surface, the one closest to us. And so this normal vector is actually pointing somewhat into the page, right? It's not on the back face pointing out at us. It's on the near face pointing into the page away from us. And so pointing into the page, you see what my right hand's fingers do, and this is going to make a swirl like that. And now the question is, how does that sideswipe up against our existing surface? And, well, now just imagine that this point kind of travels all the way down here to where the boundary is, or near where the boundary is anyway, and these swirls along the way let me get rid of that curve there, but that's going to make an orientation as I have it drawn that way. Okay, now how are we doing so far? We still haven't figured out, we haven't even talked about the new surface yet, but does everybody see how I got my boundary orientation? Okay, now that I know my boundary orientation, I'm going to clean up my picture. Let's get rid of all that. I don't need that anymore. Now we're going to consider our new surface. Our new surface is this thing. And which way does it go? Okay, well, I've got two different options. This surface might be oriented upward, might be oriented downward. I don't know. What I need is to pick the one that gives me the same boundary orientation. I need to know which one is going to make it go the same way that my original surface did. Is that right? So you consider your options, and okay, hypothetically, I suppose we could try it. Let's get it wrong first, just for fun. Let's see. I don't want that mode. I'm going to do like this. Okay, so getting it wrong just for fun. What if my normal on my new surface was upward? Well, if my normal on my new surface were upward, right hand, thumb, you look at my fingers, right? That's going to make a swirl like that. And it's just, side swipe in the wrong direction. So upward gives me that swirl, gives me the wrong orientation on the boundary. So I guess that was wrong. And then we try the other one. Other option, let's try downward. Right hand, thumb in the direction of my new candidate, right? Downward, you look at the fingers, right hand, of course. That makes a swirl. That goes that way. And that's going to sideswipe correctly. That's going to sideswipe in the correct direction. The direction that it's supposed to. It's going to give me, in other words, the orientation on the boundary that's the same as what my original surface gave it. So that's why I make this choice. Right? We pick downward instead of upward because that is what gives me the correct shared boundary orientation. What do you think? Everybody's happy? So heads up on this. I know it's just a minus sign, right? But again, not all sign errors are created equal. Some sign errors are little algebraic oopses that happen to the best of us. And are just the unavoidable human fallibility that we can't get beyond, right? This sign error, having the wrong direction on your orientation, is a significant and sophisticated and important and critical to making the theorems work part of the course material, right? It's big ideas. And so this is a big deal. And just so you know, on a 20-point question, for example, if there was a question like this on an exam, hypothetically, the orientation probably be somewhere in the range of 4 or 5 points, something like that. So it's a big deal because it's a big idea. So it's worth a lot of points. So well worth being careful, thinking it through, getting it right. And double check, because you don't want to leave those points on the table. How we doing? Everybody all right? Okay, let's see. How are we on time? We have less than a minute left. Okay, well, let's see here. Super duper quick. I am just going to do a little hand wave. At this point, we've kind of done all the new material for the course. All I have, I'm sorry, we still have Chapter 4. That'll be Monday of next week. But as far as Chapter 7 is concerned, we're kind of done with the new material. All this stuff that I have here is just going to be kind of I don't want to say summarized, but this is a way of bringing all of our ideas that we've talked about, bringing it all together in a powerful and convenient way. And then I have a bunch of examples that we're going to talk through. In particular, I'm going to talk through not just the solution to these questions, but the thought process. How you should look at the question, what your decision-making process should be that will lead you to making good choices for how to solve the problem. And we'll do that on Friday. So see y'all later. Have a good one.